Uranus, the seventh planet from our Sun, is a mysterious giant. It's an ice giant, not a gas giant like Jupiter or Saturn. This means Uranus has a lot of icy materials like water, methane, and ammonia. These materials swirl in its thick atmosphere, giving Uranus its distinctive blue-green color. The planet is tilted on its side, rotating at almost a 90-degree angle. This unusual tilt makes Uranus unique in our solar system. Each pole experiences decades of sunlight followed by darkness. Imagine a world where a single season lasts over 20 Earth years. Uranus has a faint ring system, discovered in 1977. These rings are much darker and fainter than Saturn's. They add another layer of intrigue to this fascinating planet. The most captivating aspect of Uranus is its collection of moons. Each moon holds clues to the history and formation of the Uranian system. These celestial bodies orbit the ice giant like dancers. Named after characters from Shakespeare and Pope, they add literary romance to space. Scientists study these moons to understand the forces and processes that shaped our solar system. Each moon has a story to tell, a unique chapter in the Uranian saga. Some moons, like Titania and Oberon, are large and spherical, resembling miniature planets themselves. Others, like Puck and Miranda, are smaller and more irregularly shaped. And then there are moons like Juliet, smaller and less prominent. These smaller moons may hold vital clues to understanding the intricate dance of gravity. Their compositions and orbits provide valuable data points for scientists. By studying these moons, we gain insights into the processes that shaped our own planet. They remind us that even in the vastness of space, there is always more to discover. The exploration of Uranus's moons is about understanding our place in the universe. It's about satisfying our innate human curiosity. It's about inspiring future generations to dream of the infinite possibilities. In the vast expanse of our solar system lies a small, enigmatic moon named Juliet. Circling Uranus, Juliet is one of many celestial bodies calling this turquoise giant home. Discovered in 1986, Juliet offers insights into planetary systems. Named from literary history, Juliet connects us to the cosmos. Its story adds a unique verse to our solar system's saga. Juliet's discovery was not a solitary event, but rather a part of a larger exploration of the Uranian system. In 1986, the Voyager 2 spacecraft, on its historic journey through the outer solar system, encountered Uranus and its moons, sending back a treasure trove of data and images. Among these images, scientists spotted a faint, previously unknown object orbiting the ice giant. This faint blip, a testament to the power of human ingenuity and the reach of our technological prowess, would later be confirmed as a new moon of Uranus. The discovery, a serendipitous find during a groundbreaking mission, underscored the vastness of our solar system and the potential for further discoveries. The year was 1986, and the world watched with bated breath as Voyager 2 beamed back images of a distant, unexplored realm. This robotic emissary, equipped with cutting-edge technology, provided us with our first close-up glimpse of Uranus and its intriguing system of moons. Voyager 2, with its suite of scientific instruments, captured Juliet as a small, faint object orbiting Uranus. The images, though grainy by today's standards, were groundbreaking at the time, revealing the existence of a previously unknown world. Scientists pored over the data, analyzing Juliet's size, shape, and orbital characteristics. They determined that Juliet was a small moon, only a few tens of kilometers in diameter, irregularly shaped, and likely composed of a mixture of ice and rock. These initial observations, limited as they were, provided the first clues to understanding this newly discovered member of the Uranian system. The discovery of Juliet, along with several other Uranian moons, highlighted the complexity of this distant planetary system. It challenged existing theories about moon formation and provided new puzzles for scientists to solve. Following its discovery, the newly found moon was given the temporary designation S1986U2. However, following the tradition of naming Uranian moons after characters from English literature, specifically the works of William Shakespeare and Alexander Pope, this small moon was christened Juliet. The name Juliet, taken from Shakespeare's tragic play Romeo and Juliet, seemed apt for this small moon, forever bound in a celestial dance with Uranus. This naming convention not only adds a touch of literary romance to the scientific endeavor, but also serves as a reminder of the human capacity for storytelling and our desire to find meaning in the cosmos. Juliet's name, a symbol of love and tragedy, echoes the intricate and often chaotic nature of celestial mechanics. It reminds us that even in the vastness of space, stories of connection and consequence unfold on a grand scale. Juliet, like many of its Uranian counterparts, remains shrouded in a perpetual twilight. Its surface reflects very little sunlight, making it a dim and challenging object to observe even with powerful telescopes. This lack of reflectivity is a characteristic shared by many outer solar system bodies, hinting at a composition rich in dark, carbon-based compounds. Imagine a world perpetually bathed in the faintest of glows, where shadows stretch long and deep, and the stars shine brightly, even in the daytime. This is the reality of Juliet, a world where the sun's light struggles to reach and illuminate its surface. Despite the dim lighting, or perhaps because of it, Juliet holds a certain allure, beckoning scientists to unravel its secrets. The challenges of observing Juliet from afar only make the prospect of a closer look all the more enticing. A mission to this distant moon, though a daunting technological feat, would offer invaluable insights into the nature of these icy outer solar system bodies. Based on its low reflectivity and its estimated density, scientists believe that Juliet is composed primarily of water ice, mixed with a significant fraction of darker materials. These darker materials are likely a mixture of carbon-based compounds similar to those found in comets and other primitive bodies in our solar system. This combination of ice and rock is typical of many outer solar system objects, suggesting a common origin in the cold, distant reaches of the protoplanetary disk from which our solar system formed. The exact proportions of ice and rock, however, remain uncertain, as do the details of Juliet's internal structure. Understanding Juliet's composition is crucial for piecing together the history of the Uranian system and the processes that shaped these icy worlds. Although our view of Juliet is limited, the available images suggest a heavily cratered surface bearing the scars of countless impacts over billions of years. These craters, ranging in size from small pits to larger impact basins, tell a tale of a tumultuous past, a time when the early solar system was a much more chaotic place. The presence of these craters indicates that Juliet has been bombarded by asteroids and comets throughout its history, a testament to the dynamic nature of our cosmic neighborhood. In addition to craters, Juliet's surface likely features cliffs, ridges, and other geological formations, sculpted by the forces of impact, gravity, and possibly internal activity. Each scar on Juliet's surface whispers a story of cosmic events, providing clues to the conditions that prevailed in the early solar system and the forces that shaped this small moon. At such a vast distance from the Sun, Juliet experiences frigid temperatures, far below the freezing point of water. Its surface is likely covered in a layer of water ice, mixed with the darker, carbon-rich materials. This icy surface, bombarded by radiation from the distant Sun and cosmic rays, could harbor complex organic molecules, the building blocks of life. While there is no evidence to suggest that life exists on Juliet, the possibility, however remote, adds another layer of intrigue to this distant world. Imagine a frozen wasteland, bathed in the faint glow of a distant sun, where the ground beneath your feet is harder than granite, and the only sounds are the echoes of your own footsteps. This is the likely reality of Juliet, a testament to the harsh beauty of the outer solar system, where even the most extreme environments hold the potential for scientific discovery. Juliet, like all celestial objects bound by gravity, follows a precise path around its parent planet, Uranus. This path, known as an orbit, is shaped by the delicate balance between Juliet's forward motion and the gravitational pull of Uranus. Juliet's orbit is nearly circular, meaning its distance from Uranus remains relatively constant as it circles the ice giant. This stability, a testament to the predictable nature of gravity, allows scientists to calculate Juliet's position with remarkable accuracy. Imagine tracing Juliet's path on a cosmic map, a thin, nearly perfect circle around the majestic Uranus. This orbital path, though seemingly simple, is a product of complex gravitational interactions, influenced not only by Uranus, but also by the other moons in the Uranian system. Understanding Juliet's orbit provides valuable insights into the dynamics of the Uranian system, a miniature solar system in its own right. Uranus, with its massive size and powerful gravity, exerts a strong influence on Juliet, keeping this small moon bound in its orbit. The strength of this gravitational pull determines the speed at which Juliet travels along its orbital path. The closer an object is to a massive body, the faster it needs to travel to maintain its orbit. Juliet, being relatively close to Uranus, completes one orbit in just under 17 hours, a dizzying speed compared to the leisurely 27.3 days Earth takes to orbit the Sun. Imagine witnessing Juliet's rapid journey from afar, a tiny speck of light zipping around the massive Uranus, a testament to the invisible force that governs the cosmos. This gravitational dance between Uranus and its moons, a delicate ballet played out over millions of kilometers, is a fundamental aspect of our understanding of celestial mechanics. Juliet's orbit is not solely determined by Uranus's gravity. The other moons of Uranus, each with their own gravitational pull, also exert subtle influences on Juliet's path. These gravitational interactions, though small compared to Uranus's dominant pull, can cause slight variations in Juliet's orbit over time. These variations, known as perturbations, are like tiny nudges and pulls from Juliet's fellow moons, creating a complex and ever-changing orbital dance. Imagine these moons as dancers on a cosmic stage, their movements interconnected and influencing one another, creating a mesmerizing spectacle of celestial choreography. Studying these perturbations allows scientists to map the gravitational landscape of the Uranian system and gain a deeper understanding of the delicate balance of forces at play. In some cases, the gravitational interactions between moons can lead to a phenomenon known as orbital resonance. This occurs when the orbital periods of two or more moons are related by a simple ratio, such as 1 to 2 or 2 to 3. In a resonance, the moons exert periodic gravitational tugs on each other, reinforcing their orbital patterns. These resonances, like the synchronized movements of dancers, create a sense of order and rhythm in the seemingly chaotic dance of celestial bodies. While Juliet itself is not currently known to be in a resonance with any other Uranian moon, its orbit is undoubtedly influenced by the resonant relationships that exist between other moons in the system. These resonances, like hidden connections in a complex web, highlight the interconnectedness of the Uranian system and the subtle ways in which gravity shapes the cosmic landscape. In the grand tapestry of the cosmos, Juliet, a seemingly insignificant moon orbiting a distant ice giant, holds a special place. It serves as a window into the past, offering clues about the processes that shaped our solar system billions of years ago. By studying Juliet and other Uranian moons, scientists can piece together the history of this distant planetary system and gain a better understanding of planetary formation in general. Juliet's small size, irregular shape, and likely composition of ice and rock all point to its formation in the early solar system, a time when the region around Uranus was a swirling disk of gas and dust. These remnants of the protoplanetary disk, the building blocks of planets and moons, coalesced over time, drawn together by gravity, to form the celestial bodies we observe today. Juliet's story is a reminder that even the smallest celestial bodies can hold profound secrets, offering glimpses into the distant past and shedding light on the processes that gave rise to our cosmic neighborhood. The study of moons like Juliet is crucial for refining our models of planetary formation. The prevailing theory suggests that planets form in protoplanetary disks, rotating disks of gas and dust that surround young stars. As material within these disks clumps together, it forms planetesimals, the seeds of planets. These planetesimals, through a process of accretion, gradually grow larger, attracting more material and eventually forming planets. Moons, according to this model, can form in several ways, including the accretion of material in a disk around a forming planet, the capture of passing objects by a planet's gravity, or the aftermath of giant impacts between larger bodies. Juliet's characteristics, along with those of other Uranian moons, provide valuable data points for testing and refining these models, helping scientists understand the complex interplay of forces that govern planetary system formation. Section 3. The Outer Solar System. Juliet, as a resident of the outer solar system, belongs to a family of icy worlds that hold clues to the conditions that prevailed in the early solar system. These distant bodies, far from the sun's warmth, preserve a record of the composition and dynamics of the protosolar nebula, the cloud of gas and dust from which our solar system formed. Studying the composition of these icy worlds helps scientists understand the distribution of elements in the early solar system and the processes that led to the formation of different types of planets. The presence of water ice and organic molecules on these bodies also has implications for the potential habitability of other icy worlds in our solar system and beyond. Juliet, though small and distant, contributes to this broader understanding of the outer solar system, a region rich in scientific potential and yet to be fully explored. Despite the valuable insights gained from telescopic observations and the Voyager 2 flyby, much about Juliet remains unknown. Its exact composition, its internal structure, and the details of its surface features are still shrouded in mystery. Future missions to the Uranian system, equipped with more advanced instruments, could provide a closer look at Juliet and its counterparts, revealing their secrets in greater detail. Imagine a future mission to Uranus, a spacecraft orbiting the ice giant, sending probes to its moons, analyzing their composition, mapping their surfaces, and searching for signs of past or present activity. Such a mission, though technologically challenging and costly, would be a scientific treasure trove, revolutionizing our understanding of these icy worlds and their place in the cosmic order. Until then, Juliet will continue to orbit Uranus, a silent sentinel holding clues to the past and beckoning future generations of explorers to unravel its mysteries. In the grand cosmic ballet of our solar system, where giant planets twirl with majestic grace and their rings sparkle like celestial diamonds, it's easy to overlook the smaller players on the stage. Yet these seemingly insignificant bodies, like Juliet, hold within their icy embrace secrets that can unlock profound truths about our cosmic origins. Juliet, a small dimly lit moon, serves as a stark reminder that size is not a measure of scientific significance. It's a testament to the fact that even in the vast expanse of space, every object has a story to tell, a history etched into its craters, its composition, and its orbital dance. By studying these smaller bodies, we gain access to a wealth of information about the processes that shaped our solar system and the conditions that prevailed in its tumultuous youth. The exploration of these tiny worlds is not merely an exercise in scientific curiosity. It's a journey into our own past, a quest to understand the forces that gave birth to our planet and the countless others that populate the cosmos. As we conclude our exploration of Juliet, we find ourselves not at a point of closure, but rather at the precipice of further inquiry. Despite the valuable data gathered from telescopic observations and the Voyager 2 flyby, many questions about Juliet remain unanswered. Its precise composition, the intricacies of its surface features, and the details of its formation and evolution are still shrouded in mystery, waiting to be unveiled by future missions and technological advancements. What secrets lie hidden beneath Juliet's icy shell? Could there be evidence of past geological activity, hinting at a warmer, more dynamic history? These questions beckon us to venture further into the Uranian system, to send probes and landers to its moons, and to unravel the mysteries that still hold sway over these distant worlds. In the intricate choreography of the Uranian system, Juliet plays a small but integral role. Its orbit, shaped by Uranus and its fellow moons, shows the delicate balance of cosmic forces. Studying Juliet's motion reveals the elegance of celestial mechanics and our connection to the cosmos.